So what did we do last class? So last class, we discussed how we can compute one way we might compute volume. Of a solid, whatever that means, some object in 3D space, so three-dimensional space. So we did it a little different in how lots of calculus books are written. Lots of calculus books are written, even the one that we use, in a very procedural way, sort of like, here's a formula for this. We call it the disk method. Here's a formula for that. We call it the washer method. I don't like to do it that way because, again, my philosophy is that memorizing formulas doesn't make you a good learner. It doesn't make you any better. It doesn't increase your brain capabilities. And if anything, all it can do is make you do well on exams. But I don't want you to memorize things. I want you to understand things. I want you to get where they're coming from. And so that's why I discussed the topic the way that I did. So the homework that I posted is going to ask you some questions about computing volume. And then there's some themes that pop up. So these themes will help you, so to speak, solve more problems using deductive reasoning than memorizing a formula will ever do. So just a reminder, that today we start by studying volume. From a different perspective. So the way we studied volume last class is we thought about taking a solid and slicing it into a bunch of really small pieces, looking at each piece, approximating its volume with a standard shape, and then adding those approximations together. And then when you add those approximations together, it is a Riemann sum, and hence we can then take the limits of that Riemann sum to obtain an integral. So what we want to do today, real quickly, is we want to use these same ideas, but we want to study volume a different way. And then we're not only going to look at volume, we're going to look at some other geometric ideas. So let's motivate this with sort of some sort of picture, if you will. Before we do that, does anybody want to say anything about what we talked about on Tuesday? All right, so let's consider a solid that we talked about, or something similar to what we talked about on Tuesday. So if you look at the very beginning of class on Tuesday, what we did is we drew a picture and we talked about slicing it. What we'd like to do today, so let's go like this. So let's start with the general idea of how we were getting these shapes. So one way we were getting a solid is we were taking sort of some curved region. Maybe I have this function on some point, you know, from A to B. and I look at this region under there, and if I rotated it, I would obtain some solid. And so this solid, you know, if we try to sketch it good, would look something like this. Maybe you want to think of this as some sort of like vase. So again, we take that region, we leave the piece that's attached to the x-axis fixed, and we rotate it around the x-axis. And we can think about how did we think about the volume. We thought about taking these vertical slices of this shape. So if you want to think about how that would be constructed, you might say, okay, I'm going to take this rectangular strip right here, and I'm going to ask myself, what happens to this rectangular strip as I rotate it around? Okay, thanks. See you later. Bye. So my kid, she's talking to me. So if I think about that red rectangle, what happens to that as it rotates around? Well, the bottom of it stays fixed and it rotates around, and what it does is it creates sort of this circular disc. So this strip when it rotates becomes a circular disc. So that's kind of how one way to interpret this. So the question you might ask is, you might say, okay, well, what happens if we took a different strip? Instead of slicing it vertically, what if we took horizontal slices? So you might ask yourself, why not use a horizontal slice? And turns out that you can. The only issue is it's just that the formula may be messy. So we might have messy formulas. So if for lack of more description, just think about this. Why was it smart of us to take this circular disc? Because we can get information about this thing. You know, what was nice about this right here is choosing these vertical strips. We know what this point is. This is x comma f of x. So that gives us information on the geometry of that particular disc. But if you think about it, if you tried to take a horizontal slice instead of a vertical slice, it's not obvious at all how you might obtain a formula for the size. So the best way for you to understand that is to actually try doing it, not just listening to me, but try. Okay, so notice I use the word may. Well, that's because in some situations, there is a simple formula. So let's illustrate sort of what we mean by this. And perhaps the best way to do this, because it sets up for what happens later, is to consider the following problem. So if I draw my XY axis, I want to imagine a similar scenario. So I have some function right here. And for simplicity, I'm going to draw it sort of kind of boring. It's going to look like this. And so let's call this A, let's call this point B. And what I'd like to do now is I'd like to take this shaded region I'd like to take this red shaded region and I would like to rotate it. This time, I'm going to rotate it about the y-axis. And when I rotate this region about the y-axis, I get sort of like what you might think of as like a volcano sort of type solid. So we get sort of this shape. It has a hole up top. So we have a hole here. And you might imagine that this thing sort of has this background piece to it. This sort of flow with it. And so the question is, what is the volume of this object? Now, of course, when we say there's a hole, what we mean is that you have something like this. And again, it's very difficult for me to try to sketch this on these pads, but there's no shortage of beautiful pictures in your book or on the internet that help us understand this. Now look, I could have gotten a similar shape by rotating a curve around the x-axis, but the point I want you to ponder about this is that there's another way we can sort of slice this creature. Because now, if I think about a vertical slice, if I think about taking some slice and asking what happens to this slice here, let me take this little rectangle and ask what happens to this rectangle. So I want to know, whenever I rotate my shape, if I only concentrate on that little green rectangle, what happens to it? Well, what it does is it becomes what we like to refer to as a shell. So if I go to the next page and I think merely of, let's draw the picture again. But this time, all I want to do is ask myself, what happens to this green rectangle when I rotate that? I don't care about anything else. I want the green rectangle. So let's just assume it looks like this. And when I rotate this creature around, what it does is it generates this shell-like thing. It generates something that looks like this. Well, so again, it's hard to draw these creatures, but you would imagine that this is some sort of thin strip. So it has a little thickness to it. Maybe let me try drawing that a little better. Bear with me. I am no artist, that's for sure. So again, if I imagine what happens to this thing, I imagine it looks something like this. But it has a little thickness to it because it, of course, is a rectangle. So if I try to sort of color this in, this is sort of like the top of it. One way I can get you to imagine this is, I would encourage you to think, you know, rubber band, or you know, ring, like a wedding ring. That's the kind of geometry we're looking at with this piece. So if you can see me, imagine that this pen represents my rectangle, and what happens when it rotates? Well, it comes out of the paper and then out and around, back in, and then through the back and out and around. And what it does is it traces out this, what we like to call a cylindrical shell, is the mathematical term for this. So what this does is this suggests we can approximate solids by cylindrical shells. And again, if you go to your book, there are some very nice pictures that help illustrate this. There's good videos on the internet. I highly encourage you to go investigate. Does anybody have a question or a comment? Concerns? Okay, so why would we think this is interesting then, that we can approximate a solid by a bunch of cylindrical shells? Well, because it turns out the geometry of these things is often very simple. So here's the key idea. Oftentimes, the volume of each shell results in a quote unquote simple formula. So let's see why. To see why, take your shell, which is like your rubber band type thing. It has a little bit of thickness. So it has some thickness to it. And if you're kind of confused by what I mean by that thickness, let's take scissors and let's slice it right here. Slice. So what I want to do is I want to cut and lay flat. And when I do that, my rubber band, or my wedding ring, if you would imagine, if I lay it flat, it just becomes this. It becomes this. Again, imagine, take a gum band and cut it and then lay it flat. It looks like a rectangular block. Take a wedding ring and imagine you cut it and hammer it flat. It becomes a rectangular block. And so do I say that the geometry is often simple? Well, look at this. We can tell you what each one of these things is just by looking at the picture. Remember, the height of this is the function at some given point. So this is f of x. The distance from here to here, well, we know it's a circle, so it's 2 pi times the radius. Well, what's the radius? The radius in this case is 2 pi x. Now, why am I getting x? Well, if we're going to go back a slide, and we're going to see why it's x. If we go back a slide, let's just approximate this. Let's say that this is the point x. Well, then what's this point right here? This is x comma f of x. So that means that the radius of this circle is x. The radius of this thing is x. And its height is f of x. And so what we can also do is we can say that this rectangle has a little bit of thickness. We can say that the thickness of this rectangle, you remember how we would do this, we would say x sub k and then x sub k plus 1. But for short, we might use this symbol to talk about its thickness that you will hopefully remember from last term and even this term, I guess. We could say that this guy has a thickness of delta x. Now remember, you might be thinking, well, how is that x? You're getting confused. This is an approximation. We're approximating a solid with this cylindrical shell. So we don't have to be precise here right now. Because what we know is this approximation, when we take the limit, will become precise. So not only do we get these geometric objects, we also get, and this is very important as well, we get what this is. This thickness is our delta x. So if f is simple, the beauty of this is the volume of this piece. Of the shell is nothing more than 2 pi x f of x delta x. Length times width times height. So once again, the big theme of the beauty of limits will show its face. If we can do this for this shell, this means we can do it for any number of shells. And this means we can construct a Riemann sum. Does anybody have a question or a comment? Okay, so let's make that sort of more precise. So let V be the actual volume of the solid. Then V is approximately the sum of all the pieces. We'll call V sub k. K goes 1 to n. So here, V sub k is the volume of kth shell. That's what we just showed you how to compute. And what's more important is, well, let's not say and yet. Let's be a little more sort of how this works. So if this is approximately this, then this is equal to this sum, which we found 2 pi x f of x delta x. And remember, we have to be very careful. We now have to put these subscripts in if we want to be precise. And what's important is this is a Riemann sum. And so what we can conclude, because of the definition of the integral, and if we make assumptions like f is continuous, which we do here, this limit exists. So passing to the limit, we obtain the volume is in fact equal to the integral from a to b of 2 pi x f of x dx. So there's a lot happening here, but the general theme is right on this page. And this is a theme that we've seen numerous times now, not just with volume. We saw it with area. We saw it with absolute values. Or I'm sorry, not absolute values, with average value. We're going to see it later with arc length. We're going to see it with pressure. This amazing idea that if we want to have information on the whole of something, what we do is we chop it up into pieces and we examine the pieces. And then we say, okay, if I can get information on each piece, then I can add all those pieces back together. And that gives me an approximation. But then if I let the number of those quote unquote pieces, those rectangles or those discs or those washers or now these shells, if we take the number of them and let it go off to infinity, calculus, this marvelous thing, allows us to get a precise value. So this formula right here has a name in most textbooks and doesn't ours. This is often called creatively the shell method. Does anybody have a comment or a question? All right, so excellent. Let's do an example before we move on. So so the region bounded by y equals 2 square roots of x. X equals 1 and the x-axis is rotated about the y-axis. And what we do is we obtain a solid. And we want to determine its volume. Let's draw the picture. The square root of x times 2 has a graph that looks like this. Oh. When you plug in 4, it spits out 4. The graph looks like this. And so the region we are interested in is this guy. We're only interested in what happens when x equals 1. So if we put 1 here, we're interested solely in this region. So that's the point 1, 2. So if we rotate this region about the y-axis, and we'll enlarge it for beauty's sake. If we rotate this, what we get is we get something like this. So we're going to have inside, it's going to look like this. So, and then this is going to look like this. So it sort of has this, maybe we'll try to use a different color here to give that there's this hollowed out the thing that comes inside to a point. Sort of like that. So this is what our shape is. It almost, imagine it looks like a cylinder with this sort of pointed thing hollowed out of it. And we'd like to know what the volume of this creature is. Now, you could probably use the methods of we learned last class, but we're going to use the shell method here. And so what we know is that the volume is the integral from 0 to 1 of 2 pi x times f of x. So f of x here is 2 square roots of x dx. But just to be clear what's happening here, this is my f of x. And so if you do some basic algebra, this 2 times 2 is 4. So the 4 pi can come outside, and then all you're left with is the integral of x times the square root of x, which is x to the 3/2. And so this becomes 4 pi times 2/5 x to the 5/2 from 0 to 1. And we can be very careful how we do this if we'd like. And so if you do the computation, you get 8 pi over 5 is the volume of that particular integral. So take a moment to think about that and ponder if you have a question. And let me know.
Hey, Dr. O'Grady.
Yes.
I have a question. So on the The My Math Lab problems,
Yes.
I've been doing a few of these, and on some of them, they integrate with respect to y
Yeah,
rather
yeah,
than.
yeah, you can. That's absolutely right. So that would be slightly different though. You can integrate with any variable you want. And you can set these problems up in many numerous ways. So if that's why I was very careful. Look at the wordage I'm using. If you go back a few slides, I'm saying one way we might do this, or one way to attack it is through this perspective. You can absolutely compute the volume of these things using different methods. There's a good rule of thumb, though, to have, is that if something's rotated around y, the shell method usually leads itself to easier formulas, algebra. And then if it's revolved around x, often the washer or the disk method gives you the easier formulas, if you will. But those are not rules. Those are just sort of good themes to follow. So I think what you're suggesting is that there are problems where even if they say rotate around this curve, I mean, look, I didn't go into complete detail. I don't necessarily have to revolve around the x-axis or the y-axis. If you do enough practice problems, you'll see problems where they ask you to revolve it around anything, like a line like 3x plus 2. You can rotate a region around anything. Your job as the problem solver is to figure out how, look, we are showing you ways to take a solid and compute its volume. In order to use any of these methods, you have to figure out how to describe your volume in a coordinate system so that you can take advantage of this. Now, the problems we're doing right here, these are just textbook problems. They're ones that are created to help you build confidence with these formulas. But in general, these problems can be very difficult. It's one of those things, like if you look at these sections in your book, there's usually like 60 to 70 problems in these sections. And the reason for that is that's how we learn this stuff. You know? And if you look at the homework for that matter, Paul, let me see where it's at. Oops. I just lost my shortcut. Where is my summer stuff? Oh my God. I just lost my folder. Oh, there it is. If you look at the assignment, for example, what problem is it? It's not on there. It's on a different song. Okay, I apologize. But you know, if I give you a curve and I ask you to rotate it around the y-axis, and then I ask you to rotate it about the x-axis, in general, that's going to generate two completely different solids. And then circling back to, I think, your original point, Paul, your original point was, well, they were integrating with respect to y. Well, that's fine. You can do that as well. If I wanted to use the disk method on this problem, that's exactly what I would have to do. So let me explain that real quickly. And I think it'll help. So suppose I wanted to use I shouldn't say to use. That's not good wordage. So alternatively, we might use a horizontal slice. So if I draw my picture again, instead of using that, I'm going to draw it a little a little bigger. So we're essentially looking at this sort of shape. So this would be the point 1, 2. Kind of drew that funky. So if instead, if I used, remember the region I'm after is this region right here, which I'm going to shade in red. So to use the shell method here, that would require a vertical slice. Instead, I want to use a horizontal slice. So let's put that in green. If I use a horizontal slice like this and ask myself what happens to that slice, well now, Paul, if that slice is horizontal, when I rotate it, it goes out, back, around, and through. And in this time, it creates a washer, if we look at it from this perspective. So when I rotate this slice around the y-axis, so the slice here generates a washer. So what's it going to look like? It's going to look like, well, it's going to be very flat, like this. And so it has a little bit of thickness. What's its thickness? So you can think about this as like a penny with a hole drilled through it. What's its thickness? Its thickness is this thing right here. So let's get some different, let's call this dy. Why am I going to call it delta y? Because it's a change in y. That's vertical's my y, right? And then how do I get information about, say, this point? Well, what is this point here? This is the point x comma 2 square roots of x. Now, how do I get information about, if I want to know the radius of this, if I want to know the thickness of this? Well, if this point is x, and this point is 1, what is this distance right here? This is the distance 1 minus x. So let's put that over here on our little washer. If we make the same sort of, this is my delta y. The thickness of this washer is 1 minus x, or like the distance from here to here. More generally, that tells us that this distance from here to here is x. So what is the geometry? What is the volume of this guy? So let's call this the kth washer. What is its volume? Well, this is, given the information we know that this guy has pi times radius squared. What's the outer radius? Well, that would be 1. So you might have to take a moment to come to terms with this. So this would be pi times 1 squared minus the inner guy, which we're taking out, which is pi times x squared. That is the area of the top, and then it's times delta y. So if you simplify this, this becomes pi 1 minus x squared delta y. Now, if we're being very technical, we should call this x sub k and call this x sub k, these subscripts, and this should be x sub k here. But what you see here, Paul, is a dilemma, because I'm using 2 different variables, and that's not good. I have a y and I have an x, and I can't do that. I mean, you can't go to the store today and try to pay for a pair of shoes with $70. If you buy a pair of shoes, you can't pay 30% of your shoes in Russian rubles and the other 70% of your shoes in United States dollars. That's not how it works. You have to pick a currency. So down here, the problem is we have X's and Y's, and we have to decide how we're going to do it. And there's a correct way and a wrong way to do this. Notice, how am I going to approximate my shape if I have horizontal slices? Well, if I have horizontal slices, Paul, that means I need to stack these creatures together. And so if I follow the theme I was doing before, what this does is this creates an integral where we're adding up in terms of y, not x. So this is where the difficulty lies. So before I go to the next page, let me ask you this. Do you have a question about anything on this page?
No, I think I'm good. I was just curious about using integration with respect to x and y.
Right. Okay, so we're going to build to that. Here's where we're coming with that. So this gives, what we did above, this gives an integral in y. So thus, the actual volume is approximated by the sum of these VKs. Now, what are these VKs? Well, we just told you what they are. They were pi, right? And then it was 1 minus x sub k squared dy. But the variables don't match. So what we need to do is we need to figure out how is x and y related. And if you go to the original description, what do you have? You have y is equal to 2 square roots of x. What does that mean, Paul? That means that if I divide both sides by 2, I get y over 2 is the square root of x, which tells me that x is equal to y squared over 4. Which means if I want to get everything in the same letter, same variable, this becomes pi. And now this is 1 minus y squared over 4, quantity squared dy. Which of course is pi times 1 minus y to the 4th over 16 dy. And so if you want to sort of use this approximation to get an integral, we have to send n to infinity. So if I go to the last page, where does y start and end? Y starts at 0 and it ends at 2. Yikes. Okay, so if I go back to this page, this means if I take a limit, what is v? V is the integral from 0 to 2 of pi, and then it's 1 minus y to the 4th over 16 dy. And what is this integral? Well, this is pi, and then of course you get y, and then minus y to the 5th over whatever. What's 16 times 5? Well, we'll just write it like that. Well, okay, so what's 16 times 5? If you don't know, you go to a calculator or do it in your head. So this is, where's my eraser? So 16 times 5 is what? It's 80. And this is from 0 to 2. And so when I plug in 2, I get 2 minus 32 over 80. And then when I plug in 0, I get 0. So what do I obtain? What is my answer here? Well, now you have to just go back to your heydays of basic arithmetic. You find a common denominator, or I guess you can go to a calculator. Most calculators can do this now. And if you take 2 minus 32 over 80, believe it or not, what you get is 8 pi, or you get 8 over 5. So this is 8 pi over 5. Whew, that's a lot happening there. But we got the same answer. 2 ways to get the same answer. Does anybody have a question?
So the disk method and the shell method are sort of like perpendicularly complementary.
Well, okay, there's even a better way of saying that. It's not that they're perpendicularly complementary. They're actually the same thing, but you're just viewing them from 2 different perspectives.
Right. So if you had something that you were rotating about the x-axis, if you wanted to use the disk method, you would integrate with respect to x. If you wanted to use the shell method, you would integrate with respect to y, correct?
That's correct. That's correct. Now, let me caution you. Okay, say that again.
And then if you wanted to rotate something about the y-axis, if you wanted to use the disk method, you would integrate with respect to y, and the shell you would...
No, you had it backwards.
I had it backwards.
Yeah, rotating around the y-axis, the disk method will become integrating with respect to y, and then the shell method would be integrating with respect to x, and then vice versa for the washer and disk method.
Okay.
And here's the thing, what happens, this example doesn't illustrate it as much. I didn't need this stuff in purple here on this page. You could have done the problem without that. I was just trying to show you where it comes from. But you could have just did the algebra and figured out the red on your own. What usually happens, though, is one method is much simpler algebraically and calculus-wise than the other method. Do you understand what I'm saying? So depending on the relationship up here, so if I take this relationship right here, this solving for x and leaving it in terms of y or whatever, that's what gives you the algebraic relationship. If I had to integrate with y and that was a complicated expression, it's possible I might not even been able to solve for x. So there's lots of complications that can happen here. Does that make sense? I don't know. I mean, look, I shouldn't even ask that. That's a terrible question as an instructor. Does that make sense? Because look, none of this makes sense right away. I keep telling you this, but it just doesn't. This is hard crap. But with effort and lots of effort, you guys can get it. This is a good time for me to remind you of the O'Grady philosophy. And I can't say this enough. Doing well in a class like this, in higher math courses, in science courses for that matter, it really isn't about how smart you are or how intelligent you think you are. I mean, that helps, of course. Just like playing football, it helps to be fast. Playing soccer, it helps to be fast. Those help, but they're not absolutely imperative. The number one thing you have to succeed and to learn this stuff and to learn organic chemistry and to learn, physics and to learn biochemistry, you have to be willing to sacrifice your free time. Because frankly, and pardon me for swearing, this is hard shit. You don't just learn this in 5 minutes. You just don't. No one does. And some of you might say, well, my tutor's real good or my friend is good. Yeah, you know why they're good? Not because they're Einstein, but because they've seen it before. They've done it before. And they've likely to become good at it. They've likely done it over and over and over. I mean, you got to put things in perspective. I've been doing this for like almost 20 years now, almost on a daily basis. So of course it's going to be easy for me. It's what I do. You guys are trying to learn this. One of the big mistakes you make is you think, for whatever reason, that it takes 20 minutes to learn this. And unfortunately, it just doesn't. It takes a heck of a lot more time to learn this than that. And so that's why I always tell students, being able to major in the sciences isn't about how smart you are. It's about how willing you are to sacrifice your time, especially if you want to do well. If you want to earn good grades in a class like Calc 2, it's about sacrificing time, not about your IQ, although that helps if you believe in IQs. But I don't know. Do you have any questions about this? I like going off on my little tangents. I miss not being in class and screaming and yelling with everybody. It's a damn shame. The corona has us separated. All right, any questions about this? Paul, do you have any more comments since this was your question?
Nope, I think you explained it pretty well. Thanks.
Oh my God, look at that kissing of the proverbial you know what. Very well, Paul. All right. This is good stuff. Now look, here's another thing. This often comes up. People will say, well, why do people use this in everyday life? Well, some do, yes. Will most? No. But if you argue, is it worth learning because you're never going to use it, then what's the point even going to school? Most of you 10 years from now are going to say, hey, I don't remember doing, I didn't do this in school. What you're kind of doing right now, and for many careers, this is what they want, is you're providing evidence that you can learn difficult things. I always share that story. I had a professor who used to always laugh because he would say, you know, the kids that want to go to med school would say, why do I have to take all this math? And his point was just perfect. He says, why would I trust you to cut me open and do things if you couldn't take the time to learn how to compute the volume of something? It's not just about learning about volume. That's almost a side note. It's about problem solving. It's about taking a conceptually difficult idea, understanding it, and using it to formulate and solve new problems. Because these same ideas that you see in this purple, this chopping up crap, that's what engineers use all the time to measure like strengths of beams and forces on dams. So this is not just crap for crap's sake. And so does anyone have anything else to say about this example before we move on? Okay, so let's move on to use this theme in something else. So I forget who it was. I want to say it's this professor from Cornell named Steven Strogatz, who's written a lot of great books. I think he calls integration, he calls it like the slice and sum strategy, because that's really what it is. We slice something up, we analyze the piece, and then sum them all back together in terms of an integral. So the idea of slicing, and I'm going to use it in the colloquial way here. So what I'd like to do is I'd like to consider a curve. So let's draw one. Let us draw a curve. So let's just say, here's my curve, and let's just pick 2 points. I don't know, for lack of a better word, I'll call one A. I'll call the other B. And essentially what I'd like to know is the following. What is the length from, let's call this point capital A, and we'll call this point B. I mean, this is a very perfect natural question. What is your distance traveled along a curve? I mean, you guys get in your car and use GPS all the time. Someone has to know how to answer this question. Now, if I asked this question to a bunch of 5th graders, they would come up with a real cute answer. They would say, oh, let's take a string and let's match it up to this curve, and then we'll take our string and move it over to a roller and stretch it out, and we'll see how long the curve is. And I would say, that is great. Very smart of you 5th graders. But then I would ask them the next thing, well, what is the distance traveled by an airplane that's flying from China to Chicago? Are they going to put a string on the back of the airplane and then run all the way to Chicago and measure the other end of it? Is that how they're going to determine the flight path distance of an airplane? Or how are they going to understand the trajectory of something like the rocket that just launched last weekend? When I go running at the park by my house, if the GPS satellite up there that tracks my distance didn't think about the hills, it might think I'm only running a straight distance. I mean, you can imagine the distance, if I walk straight from A to B, is going to be much shorter than if I went down the hill and then back up, right? So this is a very interesting and practical problem. And luckily, calculus gives us a way of answering this problem, and it's, well, it comes down to integration. So we can define the length as follows. So part 1, slice up the curve into n pieces, just like we did before. Okay, then once we slice those pieces of the curve, let's give them names. Let's call them, I don't know what we'll call them. We'll call them S sub 1, S sub 2, S sub n. And then we will approximate each piece with a straight line. Of length L sub 1, L sub 2, L sub 3, L sub n. That's not hard to do. That's actually easy to do. You guys know how to find the length of a straight line. You can use, well, you guys learned it as the distance formula, but it's really just the Pythagorean theorem. And then once we have these lengths, we can construct a Riemann sum. And then lastly, we can send n to infinity to get an integral. I mean, this is the strategy we've done numerous times now, and we're going to do it again. And it's a beautiful strategy. So let's look at this in detail now. Please interject if you have a question. So let's draw some pictures. Let's take, and I'm going to zoom in on my curve. So here's my curve piece. And then I'm going to take 2 points on that curve because I'm going to make this little, I'm chopping it into pieces. So remember, what is the actual length of the curve? The actual length of the curve is, we call it S sub k. So we'll call that S sub k. And then we have a line that connects these 2 points. We gave this the name L sub k. That's the length of this guy. That's kind of ugly. Let me fix that. So that's L sub k. And so here we know that S sub k is approximately L sub k. Now, let's call this point right here. Let's put our coordinate system in here somewhere, just so we have it, so we can label this very wisely. So if this is our x-axis, and then of course we have our y-axis, maybe it's over here somewhere. Let's give this point a name. We'll call, remember how we do this, we can call this guy x sub k, and we can call this guy, the next guy would be x sub k plus 1. Or maybe you don't want to do it that way. Maybe you want to do it, I mean, it doesn't matter really. Now, one of the things we learned in Calc 1 was this very powerful thing called the mean value theorem. And what the mean value theorem says is that there is a point on this blue curve where the tangent line has the same slope as the line connecting the 2 points, the black line. So let's write this down. This is very important. So the MVT says, the mean value theorem says, there is a point C sub k where f prime of C sub k times the quantity x sub k plus 1 minus x sub k. We gave a name for this, and then that's equal to f of x sub k minus f of x sub k plus 1. So there's names we gave for all these things. So let's remind you, this guy right here, this would just be our delta x. And this guy right here is just your delta y. Now, what is L sub k? Note, and this is just a Pythagorean theorem, L sub k by definition is the square root of delta x squared plus delta y squared. That's the Pythagorean theorem. If you just draw a triangle here, this is true. So using some algebra, you can rewrite this right here. This guy in red, if I factor out a delta x squared, it just becomes delta x, and then you're left with 1 plus delta y over delta x squared. That is just algebra. That's factoring out a common factor. It looks ugly, but I guarantee you if you distribute that delta x back into the radical, you get the same thing. And so what you can do then is you can replace this dy over dx using this mean value theorem thing here, and this becomes delta x times 1 plus f prime of C sub k quantity squared. Now again, there's a lot happening here. No one's pretending this is easy. You won't learn it by reading it out loud. You won't learn it by reading it to yourself. The only way you'll learn this is if you actually get out a writing instrument and you do it. You do it. You might have to go review the mean value theorem. That's okay. Now, the beauty of this algebra we got is we see our Riemann sum. It's screaming at us. Now I have something times delta x. That's all I need for a Riemann sum. So we can put all these pieces, right? You know, here's the metaphor here. Right now, I'm building a puzzle. You guys know what a puzzle is. You take it out of the box, you throw the pieces on the floor, and what's the first thing you start doing? You start organizing pieces. You say, these ones have similar colors. Or you say, these are edges, these are corners. You start organizing. So what I'm doing on this page is I'm organizing what I can get from this picture. What can I see from this picture? Granted, it's not the prettiest picture, but what's all the information I can deduce? So I'm writing down important information. Those are the pieces to my puzzle. Here's my corners, here's my edges, here's my interior. And now what I'm going to do is put the puzzle together on the next page. So when I put it together, we have the following. If L equals the actual length of the curve, L can be approximated by these L sub k's. And we know what these L sub k's are. These L sub k's are the square root of 1 plus f prime of c sub k, quantity squared, delta x. And this is a Riemann sum. Oh, by the way, hold on. This is a lie. There's a slight lie here. These aren't equal signs. These are approximations. This is approximately. This is equal sign. This square is under the square root. And so what we can conclude is that when n goes to infinity, the length is actually this integral. Integral from a to b of 1 plus f prime of x dx. Yowzers. There's a lot happening there. Does anybody have a question about this? So you now have a very nice formula for how to compute the length of a curve. Now the formula is nice. That doesn't mean it's easy to use.
I'm sorry, I was writing down the formula. When it's in the Riemann sum form,
Yes.
the quantity in the radical is squared.
Correct.
How come it's not squared
Should
once
be,
it's...
because I'm a numbskull and I forgot to put it in. That's why.
Okay.
Or I can lie and say that I was waiting for you to ask. No, I absolutely forgot. There you go.
Awesome.
Apologies. Very good, very good, very good. All right, any other questions about this creature before we do an exercise? Okay, so as you would imagine, the square root popping up here is likely to give you many difficult integrals, and we'll find out right away that it does. And that's why if you look at the homework, there's a couple problems with arc length, and 2 of the 3 are quite difficult because it requires some very ingenious algebra on your part. So I'm sure you'll have questions about that on Tuesday, and that's the purpose. But I really encourage you to try them first. Let's do an example, a quick one. So let's do the length of y equals x to the 3/2 on, say, 0, 1. So the length is this integral. Here we're going to go from 0 to 1 of 1 plus the derivative squared. So what's the derivative squared? Well, the derivative is 3/2 x to the 1/2. And so if I square that, I get 9/4 x. So this is the integral that I must evaluate. Comments, questions? How I got the 9/4? 3 squared is 9, 2 squared is 4. All right, now this integral is going to require that we do a little bit of a substitution. So let's, the clear way to think about this is I'm going to let u equal 1 plus 9/4 x. My du dx becomes 9/4. So my dx becomes 4/9 du. And so what does this integral become? It becomes 4/9 the square root of u du, but we have to change our bounds. Our bounds become 1. And then 13/4. So you might want to think about where that comes. So I got the 13/4 in the 1 using this starred formula over here. That's how you get the new bounds. You plug x in and get the corresponding u's. So this becomes 4/9, and then you integrate u to the 1/2 becomes u to the 3/2. So this is 2/3 u to the 3/2 from 1 to 13/4. And you're left with 8/27 times 13/4 to the 3/2 minus 1. I guess you can clean that up a little bit. If you wanted to. Right, you can know that 4 to the 3/2 is 8. And then if you take 13 to the 3/2, you can end up writing that as 13 times the square root of 13. So if you wanted to, you could clean this up a little more. You can say 8/27 times, yikes, 13 times the square root of 13 over 8 minus 1. Ugly. Does anybody have a comment, question? All right, well, I think we should stop here. You got a lot of problems to work on. Feel free to email me for help or hints. Feel free to schedule an office hour, and feel free to ask questions on Tuesday when we meet again. If you guys don't have any questions, I will say see you Tuesday.